In this video, we are going to discuss alkene forming reactions that are performed on aldehydes and ketones. Our first one is the Wittig reaction. Now, the Wittig reaction is done by reacting an aldehyde or ketone with a phosphorus ylide. An ylide is a molecule that has a positive and negative charge directly next to each other and is overall a neutral molecule. So this molecule here is overall neutral, but we have a negative charge on the carbon and then a positive charge on the immediately attached phosphorus. This particular type of ylide that's used in a Wittig reaction is also sometimes called a phosphorane. It's also important to note that this does have an important resonance form where you can form a pi bond between the phosphorus and the carbon atom, which kind of gives us an idea of why this molecule is allowed to exist at all, because it does have a stabilizing resonance form, but it is the ylide form that's going to undergo the reaction. Now, when these two things are combined, you end up forming an alkene where the double bond is formed between the two carbon atoms that are drawn out here. So we would make the alkene between the carbonyl carbon of our carbonyl compound and the negatively charged carbon of the ylide. So if we look in our molecule to the right, our carbonyl carbon is now in blue, and our ylide carbon is outlined in orange. And then we have a side product. An important note, at least one of these R groups must be a hydrogen, and also if Z and E isomers are possible, Z is going to be the major product with a Wittig reaction. So let's take a look at how the phosphorus ylide is synthesized. Another important note about the Wittig reaction is that you're usually not given an aldehyde or ketone plus a phosphorus ylide. Usually you are given the reagents that will form the phosphorus ylide, and you are meant to know that that's what's going to happen. So a phosphorus ylide is synthesized by combining triphenylphosphine with an alkyl halide. These are going to undergo an SN2 reaction where the bromine is kicked out. Which gives us our first intermediate. From here, you will see an alkyl lithiate added. The alkyl lithiate will deprotonate the carbon. To form the phosphorus ylide. So the ylide that has been formed is our reactive species. So usually what you'll see in this type of reaction is something like an alkyl halide that is first reacted with triphenylphosphine, and then an alkyl lithiate is added. In-butyl lithium is a really common one. Sometimes you see it written out as in buly, essentially. And then from there, you might see the aldehyde or ketone added. So you are meant to take these three things and interpret that you are forming an ylide. So understanding how the ylide is formed is really important so that you can draw out the correct structure. So let's take a look at the mechanism of the Wittig reaction. We're going to do some pretty heavy color coding on this slide. So in the first step of the reaction, we have the reaction initiated by the negative charge of the ylide. It's going to attack the carbonyl carbon. And when that happens, the electrons in the pi bond between the carbonyl and the oxygen are going to attack the phosphorus of the ylide. So we are going to be creating a cyclic intermediate. So the cyclic intermediate that we just formed is called an oxaphosphatane. And since we've created a four-membered ring by creating these two new bonds, we've created something pretty unstable, and this is actually going to collapse down. So what we end up seeing is the bond between the carbon and the phosphorus breaks, creating a double bond between the two carbon atoms, and the bond between the carbonyl carbon and the oxygen is going to break to form a pi bond between the oxygen and phosphorus, giving us our alkene and our byproduct. So this is the part where it's important to note that if the E or Z isomers are both possible, the Z isomer is going to predominate. So that is just depending on, which way are these two things attacking each other. So in an actual example, we're going to take cyclohexanone and react with methyl triphenylphosphonium. We're going to have the same reaction arrows that we had previously. The Ylide carbon attacks the carbonyl. The electrons in the pi bond of the carbonyl bond are going to attack the positively charged phosphorus of the Ylide. Which gives us our oxaphosphatane intermediate. So at this point, the last bit is that we break down these bonds to form our double bonds to give us our brand new alkene. So Wittig is often used in synthesis problems, and it's really important to be able to break apart an alkene and to determine how that alkene would have been created using a Wittig reaction. So this sounds a lot more complicated than it actually is. All you really have to do is imagine that you break the alkene that must have been formed. In this case, this is the only alkene, so it's pretty clear where the chemistry would have happened. And then you can create an Ylide or a carbonyl from either piece. So let's pretend that the 3 carbons at the end here came from an Ylide. Then what we would need is these 3 carbons with phosphorus and a negative charge on the carbon. These would be created by reacting an alkyl halide with triphenylphosphine and following it up with an alkyl lithiate. And then you would also need to react with a carbonyl compound, so that's going to be the other half here. So we need our benzene ring, and then we want a carbonyl where the double bond is in our product. And we know this has to be an aldehyde because there is a hydrogen here. So that's all you have to do for a Wittig reaction in synthesis. So just kind of backtrack through the alkene, identify the Ylide and the carbonyl compound, and then how would you create the Ylide. You also could have done this where the Ylide was on the aromatic portion and the carbonyl compound was acetone. So in the next one, I'm going to go ahead and erase this just so we can have a little more space. In the next one, we're going to do the same thing. Imagine breaking that double bond and then create a carbonyl and an Ylide from either piece. So let's pretend that we make the carbonyl from this part. That would be cyclohexanone. And then if we want to make the ylide from this part, we're going to need our cyclohexane ring, and then 1, 2 more carbons. It would have to be an alkyl halide that we would first react with triphenylphosphine, and then with an alkyl lithiate of your choice. And this would give us our ylide. So combine this ylide with cyclohexanone and you would get the intended product. There's another alkene forming reaction called the Horner-Wadsworth-Emmons reaction, and this is very, very similar to the Wittig reaction. It's just we use a phosphonate ester in the place of triphenylphosphine and creating a phosphonium-based ylide. The reason that we're bothering to learn this is that the Wittig reaction usually prefers to give us the Z product, but the Horner-Wadsworth-Emmons reaction is going to preferentially create the E isomer. So the formation of our reactive species is a little different here. We react an alkyl halide with triethyl phosphite, which is this compound here, to create a phosphonate ester. And our byproduct is actually an alkyl halide, because notice that we got rid of one of the ethyl groups. So from here, the phosphonate ester has to be deprotonated. So we remove this proton. We're going to use sodium hydride here. So remember, hydride is hydrogen with a lone pair and a negative charge. This is going to be able to pull off this hydrogen and create an ylide. From here, we can add in a carbonyl compound. Such as an aldehyde, and we end up creating a double bond just like we did in the Wittig reaction. So we have our alkene formed with the 2 pieces from the phosphorus ylide and the aldehyde, and then we also have this phosphorus-based byproduct which you do not need to provide.